Hello everyone, this is the second part of the 14th lecture in the series Mathematical Methods for Economics. In the first part, I had covered the cases where the exponent is any real number and the second case where the exponent is any positive integer. Now we will move to the third case in our discussion where we assume that r is a negative integer, and let's see what ramifications that has for the domain of such functions and also what the graphs look like. So let's look at this slide here. Here in this case where r is a negative integer, we can write the function x to the power r as x to the power minus n, right? So here n is any natural number, it's a natural number, 1, 2, 3, 4, 5 and so on. So when I take x to the power minus n, then my exponent r becomes a negative integer, right? And you all know that x to the power minus n can be written as 1 divided by x to the power n. Here, the only restriction that we need on the domain is that x should not be 0. Do you see that? Because because division by 0 is not defined. So otherwise, x can be any number, any real number other than 0. Okay, so let's first take the case where n is odd. Let's take some individual cases again before we move to see the families of curves in this category. So if n is odd, let's suppose n is equal to 1, then we get f of x is equal to 1 divided by x, and that is nothing. If we were to draw the graph of y equal to 1 by x, that is nothing but a rectangular hyperbola, which here will lie in the first and the third quadrants, right? And here you can see that because x equal to 0 is not a part of the domain, here there is a break, there is a discontinuity in the graph at x equal to 0. We haven't covered continuity yet, but you can see that there is a break because we can't take x equal to 0 as part of the domain. Also note here that this is a graph which will pass through 1, 1, right? And we also have symmetry here, because if the point here about the origin, we'll have symmetry, because if the point 1, 1 is a part of this graph, then the point minus 1, minus 1 is also a part of this graph. So you have symmetry about the origin. And here we can bring in the concept of asymptotes. I haven't covered that yet. Asymptote, which is spelled as ASYMPTOTE. Basically here both the axes, the x-axis and the y-axis, they act as asymptotes, which is to say that the graph of this particular function that will approach the axis but will never touch the axis. Okay, that is the idea of the asymptotes. So as x tends to infinity, y approaches 0, okay, or as x tends to minus infinity, y approaches 0, but it will never touch the axis. Similarly, you can see here that because x equal to 0 is not a part of the domain, the graph it approaches the y-axis from here and from the bottom here in the third quadrant, but it never touches it. Okay, so this was a case where n was even. Now if n was odd, if I now take n as, let's say, 2, which is an even number, then I will get the graph of the function 1 by x squared, and this is what the graph looks like. This is going to be a graph which would lie in the first and the second quadrants, right, because y equal to 1 by x squared is always going to be positive. Here also you can see that both the axes, they act as asymptotes, and this is a graph which is symmetric about the y-axis. Okay, so here you have that if the point 1, 1 both the points 1, 1 and minus 1, 1 lie on the graph. Right, so let us generalize. If you have r as a negative integer, then whatever the value of n is, the graphs will pass through the point 1, 1 for all values of n. And the second feature that I am pointing out here is that the graphs will have a break or a discontinuity at x equal to 0. And these are the common features which I just pointed out while looking at the specific cases, and we'll just look at the families of curves, but let me just quickly go through this. So if f of x is equal to 1 divided by x to the power n, then the graph of 1 by x to the power n for n even has the same shape as that of y equal to 1 by x squared. Okay. The function 1 by x to the power n, this is an even function, that is, it is symmetric about the y-axis. The graphs, in addition to passing through 1 comma 1, because there is symmetry about the y-axis, will also pass through minus 1 comma 1. If n is odd, then the graph of 1 by x to the power n will have the same general shape as that of 1 by x, the rectangular hyperbola. And here the function is odd, where you have symmetry about the origin, so that the graphs not only pass through 1 comma 1 but also minus 1 comma minus 1. And here the opposite is going to happen. So when we look at the families of curves, in the interval minus 1 to 0 and 0 to 1, because here 0 is not included, we have to break that interval between minus 1 and 1. So here the height of the graph will become larger as n increases, but the height will be smaller over the intervals x greater than 1, x strictly greater than 1, and x strictly less than minus 1. And to see why this happens, because for example, if you take a number between 0 and 1, let's say like 0.1, then as n increases, what will happen? X to the power n will decrease, right? Because if I take 0.1 squared or and compare it with 0.1 to the power 4, 0.1 to the power 4 will be a smaller number, and because here we are taking the reciprocal here, okay, so 1 by x to the power n will increase when n increases, right? X to the power n falls, which is to say 1 by x to the power n increases as n increases. And similarly, you can build up the argument for a negative x, as but here you'll have to take into account, it's easier to just analyze things in terms of absolute values. So here the absolute value of x to the power n will go down, and therefore the absolute value of 1 by x to the power n will increase. Right, and let's look at the families of functions here. So the graph in green here is 1 by x, and you can see here that for 1 by x cubed now, you can see that the height is more for 1 by x cubed for any number between 0 and 1, right? Similarly here in absolute terms, the height is more for the graph in the middle and for the one in blue, which is a graph of 1 by x to the power 5. So this is the case where you have an odd function, right? And basically the graph of 1 by x cubed or 1 by x to the power 5 will have the same general shape as the graph of 1 by x. And here you have symmetry about the origin, so that both the points 1 comma 1 and minus 1 comma minus 1, for example, will lie on the same graph. This is a family of curves that you see here on this slide, which I'm showing for n even. So here I'm showing you the graphs of y equal to 1 by x squared, 1 by x to the power 4, and 1 by x to the 6. So this is the family of curves that you get in this picture for n even. Here 1 by x squared is the graph in green here, okay? And then the middle one is 1 by x to the power 4, which has the same general shape as 1 by x squared. And you can see here that between minus 1 and 1, now the height will be more for 1 by x to the power 4 or 1 by x to the power 6 as compared to 1 by x squared. But the opposite will now be true to the right of 1 and to the left of minus 1. Okay, and here again you have symmetry about the y-axis. You have both, you can see here both the points 1 comma 1 and minus 1 comma 1, they lie on the same graph. And finally we're going to consider the case where excuse me, where r is equal to 1 by n, right? N here is a natural number, and if if r is equal to 1 by n, then our function becomes f of x equal to x to the power 1 by n, which can be written as the nth root of x. Now here I can distinguish between two cases. I can take n as odd, right, or n as even. If n is even, then I will have to place this restriction that x is greater than or equal to 0. It can't be negative. So for example, if I were taking the square root of x or the fourth root of x and so on, then here I can't define the square root, right, or the fourth root for a negative value of x, because we are here concerned only with real numbers. Negative numbers have imaginary square roots. However, if n is odd, then there is no restriction. We can take x to be any real number. So do you see how? So the beauty of this is you can see how the domains change. This just helps you think about how these will change in terms of how you draw the graphs, depending on the assumptions that you make for what R is, the specific sets that R belongs to. So, okay, let's do a quick analysis of this before we move on to exponential functions. Now, here we have x to the power 1 by n, where I'm taking I'm sorry, there's a typo here. So here n is even. So don't take this as n equal to 1, 2, 3. This will be 2, 4, 6 and so on. So if n is equal to 2, for example, you get the graph of y equal to square root of x, and you can see here that this is restricted to the first quadrant, and here we are allowing x to be equal to 0 also, because we're just looking at x to the power 1 by n for n even. Okay, so if n is odd, however, again here in the title I'll have to take odd numbers, so 1, 3 and so on. 1 does not make sense because that will just boil down to y equal to x. So let's start with 3, 5, 7 and so on. So if n is equal to 3, this is the kind of graph that you get, and here again you can see 1, 1 is a point on this graph. And here what I would like you to do is, as an exercise, probably you can take higher powers, higher even powers or higher odd powers, and build up the family of curves that you would get. Take 2 or 3 powers and see what kinds of graphs you get, and you can draw all the curves in the same graph, so it all in one picture. And that is an exercise you can do. We've covered power functions in a lot of detail now, and I think you should be able to take it from here. Also, we can extend this discussion to, we can build up cases where you have fractional exponents in general. So instead of just having 1 by n, you could have a fraction like 2 by 3, or you could even have irrational exponents. So you could have a function like x to the power root 2, but those are things we can discuss later on in the course. I think till this point things are quite sufficient for the level at which you are studying. Let me just quickly go through 2 examples for power functions, and this is just so that we have at least some problems of practice. So here the question asks you to simplify the following expression, and you have 3a to the power minus 1, the whole thing raised to the power minus 2, times 2a to the power minus 2, the whole thing raised to the power minus 1, divided by a to the power minus 3. Now here you can see if you want to simplify things, you can straight away take a to the power minus 3 to the numerator, which then gives you a cubed, right? 3a to the power minus 1 times, to the power minus 2 times 2a to the power minus 2 to the power minus 1. Now here we can use the power rule that a to the power r, the whole thing raised to the power s, is nothing but a to the power rs, right? So what will happen? 3a to the power minus 1, the whole thing to the power minus 2 will become 3a squared, right? Because minus 1 will get multiplied with minus 2. Similarly, we have that 2 times a to the power minus 2, that will become 2 to the power minus 1, because you have a minus 1 outside the brackets here. So 2 to the power minus 1, and a to the power minus 2 to the power minus 1 is nothing but a squared. Now let's simplify this. Things are already set for getting the solution. So you have a cubed here. 3 squared is nothing but 9, right? And you get a squared. 2 I've taken to the denominator, and then you have another a squared here, and that then gives us 9 a to the power 7 divided by 2. Okay, so that is a simplification. this problem, this is actually a nice problem. Let me just do it quickly because this is a kind of expression that you might need when you do the chapter on derivatives. So here you have the expression a to the power 1/3 minus b to the power 1/3 multiplied by a to the power 2/3 plus a to the 1/3 times b to the 1/3 plus b to the 2/3. You have to simplify this expression, so just open up the brackets. It's as simple as that. So we take a to the 1/3, multiply that with a to the 2/3 plus a to the 1/3, whatever you have in brackets, minus b to the 1/3 times the second expression, the entire second expression that you have in brackets. And now just start opening up the brackets. So a to the 1/3 times a to the power 2/3 is nothing but a, because you simply add up the exponents. Then a to the 1/3 times a to the 1/3 times b to the 1/3 is a to the 2/3 times b to the 1/3, plus the third term will become a to the 1/3 times b to the 2/3. And similarly, if you simplify, just open up the brackets in the second expression, you get minus b to the 1/3 a to the 2/3 plus, I've taken the whole thing in brackets, so minus is outside, so inside the brackets I have plus a to the 1/3 b to the 2/3, right, and plus b, because b to the 1/3 plus b to the 2/3 is nothing but b. And you see here that the terms in the middle, they cancel out. A to the 2/3 times b to the 1/3 will cancel out this, so this expression here also cancels, and what you're left with is just this very simple expression, which is a minus b. And that is all I have for the discussion on power functions. And this was actually quite a task to organize this lecture, because the discussion in your textbook, which is the textbook prescribed for this course, the one by Satan Hammond, Mathematics for Economic Analysis, there the discussion, and even in other books for that matter, it's quite scattered. So it was quite a task to put things together, and I hope you've been able to make sense of things. And in addition to Satan Hammond and a few other books, I've also referred, in fact today's lecture was largely borrowed from the book by Anton. The book is titled Calculus. It's a book for used by maths honors students in Delhi University. Okay, so the next category of functions that we're going to discuss is exponential functions, and this is a category of functions, a class of functions that has a variety of applications ranging from economic growth, population growth. So in economics, you just have a variety of applications. Then if we are doing a course in finance, the starting point is where you're taught these principles of compound interest. So you look at how interest accumulates over time. That is also covered through exponential functions. Then you could also look at how it's not just how quantities increase, but you could also look at population, the phenomena of population decrease, or in science the concept of radioactive decay, or for that matter, if you've been following the news on the COVID-19 pandemic, how infections grow before they peak, right? So that is often described as exponential growth. So exponential functions come in quite handy, and there's also this concept of doubling time, which you must have read about in the papers in the context of this coronavirus. And these are concepts which we will cover in this particular segment, though I won't be able to finish the discussion today, but in this particular lecture, we'll carry forth this discussion in the next lecture, which will be lecture 15. But anyway, what exactly are exponential functions all about, and what exactly does this word exponential mean? Because that is the key. You have to be very clear about this word exponential. So the point here is that a quantity is said to increase or decrease exponentially. Look at the slide here. If it increases or decreases by a fixed factor per unit of time. This phrase is very important. If you see that a quantity increases or decreases by a fixed factor per unit of time, that is to say that the quantity is changing exponentially. Okay, let me give you a sense of things. Let me give you some numbers to actually illustrate what I'm trying to say. Here I'm giving you two scenarios. Okay, so in both these scenarios, I'm calling them A and B. In both these scenarios, the variable x, which you can take as time, that changes in the same way. So you are moving from 1, x equal to 1, 2, 3, it changes by 1 unit, right? So you can think of these as days. So day 1, day 2, day 3. And in scenario A, the values that y takes, the variable y, and you can think of this as money perhaps, or in terms of corona, you know, the number of infections. But here, if you have a situation like this, basically y here, you're starting out by y equal to 2 for x equal to 1, then y becomes 4, then 6, then 8, 10 and 12 and so on. So basically what do you see? That there is for each time period, y is changing exactly by 2. So if you start out by 2 rupees, then you have 4 rupees on day 2, then you have 6 rupees. So basically every time your money increases by 2 rupees, right? Which is to say that there is a constant rate of change. This is what would be modeled by a linear function. Now in contrast, look at what's happening in scenario B. In scenario B, what is happening is on day 1, the value of y is 2. On day 2, it's 4. On day 3, it's 8. On day 4, it's 16, then 32, then 64 and so on. What is happening? Every successive time period, the value is doubling, right? It could be any other factor also. Here I've taken the factor of 2. So in every, if you take any two consecutive numbers, the ratio of those two numbers will be a constant here. So basically what you see here is geometric growth or accelerated growth, right? So the first kind of phenomenon that we see here, where we talked of scenario A, this was the one corresponding to linear growth, right? So if you have 2 rupees and 4 rupees and 6 rupees, every time it increases by 2 rupees, that is something which would be modeled by an equation like y equal to 2 times x. However, if you have exponential growth, that would be modeled by, in this case, because 2 is a fixed factor, and I'll just show you that this base here is what represents a fixed factor. So this is the kind of scenario that is represented by the equation y equal to 2 to the power of x. You have, between any two consecutive numbers, you'll have the same ratio, okay? In terms of a diagram, this is what is happening here. The line in blue represents linear growth, and the curve in red, it represents exponential growth. That's a graph of an exponential function, in this case 2 to the power x. And what do you notice here? That initially things are slow to start with, and then you have explosive growth. So the graph grows very rapidly for larger values of x. And this is in contrast to what we call logarithmic growth, where for larger values of x, you have the graph actually grows slowly. So it grows slower for larger values of x. But here, because as the x value becomes larger, when you keep when things get multiplied by that fixed factor, when things get compounded by the fixed factor, then you just have explosive growth. So this is in fact the kind of situation which people have talked about vis-a-vis the COVID-19 pandemic, for example, where before the peak was reached, the infections, they said, were growing, the infections were showing exponential growth. So this here we can say that the number of infected persons is growing exponentially if there is a fixed factor by which you see the growth taking place. So for example, today if 2 people, 2 is a number of infected persons, then day 2 there'll be 4 people who are infected, day 3 there'll be 8 people, then 16 and so on, right? So I'm sorry, it'll be, these will be the numbers, right? So exactly 2 is a factor here. Okay, so this is as far as your, I just wanted to give you a sense of exponential growth. And here we are talking of a quantity which increases or decreases by a fixed factor per unit of time. That is what I was trying to illustrate. Now, in general, an exponential function can be defined as f of t equal to capital A times small a to the power t, where both capital A and small a are taken as positive constants. And I will just show you in the next slide that it is this base here, this lowercase a, the small a, which is actually the fixed factor by which our quantity increases or decreases per unit of time. And you can see here that if, let's say, we take the function as capital A times small a to the power t, then the value of the function in time period t plus 1, by the way, in general, you could even take this as a function of x, but because we generally see how quantities increase or decrease with respect to time, that is why I have taken time as the independent variable. So the value of the function at time period t plus 1 here would become capital A times small a to the power t plus 1, right? In the power now I'll have t plus 1, and that a to the power t plus 1 can be broken up into a to the power t times a to the power 1. So this can be then written as capital A times small a to the power t times a, right? And that is nothing but small a times f of t, because this expression here, capital A times small a to the power t, this is nothing but your function f of t. So what do you notice here? The value of the function in any time period t plus 1 is always a times the value of the function in the time period t, right? And that is why a is said to be the fixed factor, right? So that is what I would like you to be very clear about. A represents the fixed factor because the value at time period t plus 1 is a times the value of the function at time period t. Now, another thing you can notice here is that we can give an interpretation to this capital A here. So if I look at the value of the function at time period 0, that is nothing but capital A times small a to the power 0, because t has to be 0 here, and that is nothing but a times 1 or a. So a here is nothing but the value of the function at time period 0. So that is also known as the initial value, and that implies that I can write the function f of t as f of 0, which is initial value or capital A times small a to the power t. Okay, so this was a little primer on exponential functions. Clearly, I'll have to devote another lecture to this topic because this was clearly not enough. There's a lot more to be discussed. And what you can perhaps think about before I wind up today's lecture is go back to this example, so look at this scenario B, and let's suppose I give you a choice. Okay, so today let's say I say that after 30 days I say that you can either get 1 million or you can get 1 rupee doubled every day for the next 30 days. So which option will you choose, right? One option is where you have 1 rupee, right, doubled for the next 30 days. So 1 rupee today, let's say today's time period t equal to 0, that will become 2 rupees tomorrow, then it will become 4 rupees, okay, on day 2 it will become 8 rupees on day 3 as per this scenario. So if I say that your money will double and we'll continue like this for the next 30 days. So would you prefer that option, or would you prefer the option where I give you straight away 1 million rupees? Okay, so think about that, and we will unravel this mystery in the next class. Thank you so much.